we have determine whether CF2Cl2 is polar or nonpolar. Which of the following hybridization schemes allows the central atom to form more than 4 bonds? So with that being said, I'm not sure if you can read the answer already. We're going to just solve A and B. So CF2Cl2, polar versus non-polar. So with this, what we have is, if you want to go ahead, so I want to write down both questions first. And which is more than 4 bonds? That is, as I said, sp3, sp3d, and sp2. Okay? So first part, we want to draw the Lewis structure of CF2Cl2. Okay? Carbon, being on the 14th column, has 4 valence electrons. Fluorine and chlorine, being on the 17th column, each have 7 valence electrons. So that's 7 times 4, 28, plus that 4 from the carbon. We're working with 32 electrons. So, with that being said, put the carbon in the middle. F, F, Cl, Cl, and then we fill out the valence. So fluorine was sharing 1 of its 7, which is why we can add 6 more. Same thing here, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7. Definitely almost missed one here on the fluorine. Okay, and then 2, 3, 4, 5, 6, 7. And carbon is already sharing 4 of its 4. Do we have 32 electrons here? Let's see. We have 3 times 4 lone pairs, and we have 4 bonds. So that's 12 plus 4, that's 16 total bond slash lone pairs. So that is indeed 32 electrons. So, with that being said, do they follow the octet rule? That I can also say for sure that is true. And do all these have a formal charge of 0? Let's find out. Fluorine's formal charge is 3 lone pairs and 1 bond, which is what it's doing. Same thing with the chlorine, is 3 lone pairs and 1 bond. And for the carbon, for it to be 0, is just 4 bonds. So all of these fit the criteria of all having a formal charge of 0. So that's the Lewis structure. Now, to know if this is polar or non-polar, actually, it would be best to draw this as its molecular geometry. Because what if I drew this like this? Now, you could argue that, wait a minute, the fluorines are pulling evenly and the chlorines are pulling evenly, so this will cancel out, which is why you need your molecular geometry. So this shape is known as tetrahedral. Okay? And what this would actually look like, if I drew it out to my best capabilities, something like this. And it doesn't even matter what I even put here anymore, because as you see, this is always going to be uneven. There's no way the fluorines and the chlorines could pull to where they would quote-unquote cancel each other out. And that's actually what I want to stress, because, so to clarify, as you can see, that bolded line is, imagine the chlorine coming out of the page. And that dashed line, imagine the chlorine going into the page. So that's what I mean by there's no really good way to draw it to where it balances out. And the reason why I mentioned this is because if you go to the periodic table, fluorine is like the strongest, one of these, if not the strongest electronegative atom at 3.98. The difference between fluorine and carbon, in fact between fluorine and chlorine, because that's really what's competing, that's 3.98 minus 3.16. So like a 0.82 difference around there. Point being that this is enough for us to say that these are going to be polar, not really polar bonds, but there's a big enough difference to where fluorine would have a higher affinity for the electrons in the chlorines. So overall, you'd see like a net, I guess, if I were to draw it, kind of like a net pull this way towards the fluorines, okay? And because exactly these fluorines can't bounce out, that's how we get this shape. Well, I mean, not this shape, but this kind of pull. And because there is a pull, you can now see for sure that this is going to be polar. And that's why drawing the Lewis structure was not enough, because had I just left it at the Lewis structure, exactly, I could argue that the fluorines are perfectly cancel each other out. Now that you see the molecular geometry, it should be a little bit more clear to be like, okay, well, now I know this wouldn't work. So now the next part is asking, which of these is more than 4 bonds? sp3, sp3d, and sp2. So for this, we need to know what that even means, okay? So this would be an s orbital, this would be a p orbital, this would be a d orbital, okay? And we're only messing with the, there we go. Oh, I think I minimized, that's what happened. We're only messing with the first d orbital, so we're going this far, according to the question. So, s, p, and d. In each orbital, it can fit 2 electrons. Okay? And now we're going to apply this to, I guess, like real life. If I said I had sp3, how many electrons am I working with? In total, 8. 8 shared electrons with me, or just 8 electrons I have. Funny enough, looking at the central atom, that carbon, this is what we actually would refer to as being sp3 hybridized. And as you can see here, only 4 bonds, which is why this would not work. sp2, 6 electrons. We're thinking of things more like this. Definitely blanked out there for a second. Like boron. Okay? That is what we're thinking when we're thinking of sp2. It does get more complicated than this. Other things can count as sp2, but this is what I want you to visualize when you think of sp2, because there's 6 electrons that can fit. But now sp3d, we're dealing with the first orbital there. All of a sudden, we're dealing with 10 electrons. For this, think of it like phosphate, because that one can break the octet rule. This right here is what comes to my mind when I think of sp3d, because we need 10 electrons that is sharing or just has to itself. So with that being said, the only one that has more than 4 bonds, that can have more than 4 bonds, would be the sp3d orbital. That will be the one, okay? Not the sp3 and not the sp2. So with that, let's see what they says. It's like sp3d allows it to form more than 4 bonds because it typically has 5 bonds. Something else you could also do is like with sulfur. This is also technically sp3d, okay? Now, with all that being said, as we reviewed, CF2Cl2 is the polar molecule according to my colleague as well. So with that, we are good to go. So we fully answered this question. Okay, so this is correct. Let's see, do we have anything else? I don't think we should. Let's find out. Okay, so it looks like we're done. And with that being said, I just want to thank you again for joining me this stream. If you have any questions or want to go over the topics that was covered today, please reach out at the link in the description below. Once again, thank you for joining this stream. You have a lovely rest of your evening, and see you next time.